Introduction to Algorithmic Information Theory and Universal Learning. Yeah, thank you. Oh. No, I don't have a mouse. No, sorry.
Yeah, hi. Yeah, I'm Marcus.
Yeah, can you unmute yourself?
Okay. Okay, can you see me now? Can everyone see me here in the room? Okay, you have to switch off the speaker. Yeah, Marcus Hutter. I was for many years, 12 years or so in Australia at the Australian National University. I'm still adjunct there and have a couple of PhD students there, but since 3 years I work at DeepMind here in London, which was quite a change. The ultimate goal hasn't changed. So if you don't know me, sort of my primary goal is to achieve AGI. I believe that the learning and planning are the key components, and to well-define learning, you can do that via compression, Kolmogorov complexity gives you the ultimate notion. So I will not really talk about sort of, my universal AI stuff at the very end a little bit, because that's about machine learning here and algorithmic information theory. So I will give an introduction to algorithmic information theory. Okay, so let me start. I presume that you all know about Kolmogorov complexity, so I will be very brief. Then I will introduce Solomonoff's universal a priori distribution and how it is used for solving actually the sequence prediction problem and the induction problem. I will briefly talk about Martin-Löf randomness, because sort of you can, if you want to divide the field of algorithmic information theory in 4 parts. One is Kolmogorov complexity, one is Solomonoff induction, one is randomness, Martin-Löf randomness, and the 4th is maybe universal search. Right? I will not really, I have maybe half a slide or so on universal search. So Levin search. Okay, and I want to cover sort of the important aspects. Then I will show how it's related to the minimal description length or minimal message length principle. I've seen that at least 2 others give talks about MDL and MML, so I will probably skip over these slides, be very brief. Then maybe the first very impressive application, more or less directly, of Kolmogorov complexity, the universal similarity metric, which is too good to skip. And then I briefly talk about AI, which is really what I care about, yeah, just mention the further applications. Okay. Oh, okay. Now. Okay, now you can all see me. Okay. So Kolmogorov complexity. So the formal definition is as follows. So forget the Y at the moment. You have a string, and you look for programs, which if you run this program on a general purpose computer or universal Turing machine, it reproduces your binary string. There are many of these programs. Print quotation mark string is one of them, but they're often shorter programs. And you look for the shortest program and the length of it, and you call it Kolmogorov complexity of X. If you have side information, Y, then you also feed that in on an extra tape on this universal Turing machine. So that would be the conditional complexity of X given Y. So the shortest program which converts Y into X. If Y is not helpful, then you would just ignore the Y, okay, which you can always do without cost. So often we talk about Kolmogorov complexity of things which are not strings. Then we have to first encode this object somewhere as a string and then ask for the shortest program. For instance, if I talk about Kolmogorov complexity of a function, well, a function could be represented as a program which maps input to outputs, and then we're looking for the shortest program. But there are choices to make, and the results may depend a bit on this choice. Often there's a canonical choice. So if I have natural numbers, of course, you just code it in some standard way. And the choices often don't matter too much, and I will explain what it means not too much. Okay, and obviously very simple strings like all zeros have a very short program. It's just a loop, and other strings like random strings can't be compressed. And this notion is nearly independent of the choice of universal Turing machine. Nearly means apart from an additive constant. I'll come back to that. It also satisfies most properties in information measure should satisfy, and I will not go into what should mean, but I will show that it satisfies virtually all properties which Shannon entropy also satisfies. So there's a very close relation between these properties and the corresponding one in Shannon entropy. Okay, a big downside of Kolmogorov complexity is that it's incomputable. Okay, and so I mean these are these two standard critiques. All it depends on the universal Turing machine, which you can counter by that the dependence is weak in a certain sense, and the non-computability. Well, I mean that's a serious issue. You have to approximate that. And I mean, we can do that in various forms. You can use actually any data compressor and regard it as an approximation of Kolmogorov complexity or MDL as an approximation. The sad thing is that unfortunately, many of the beautiful theorems which hold for Kolmogorov complexity do not hold for the approximations anymore. Yeah. So I had a funny discussion with some, I mean, I was, just a student with a professor who was applied computer science, and he really hated theory. And there was really no way of convincing him that it is useful. But then this universal similarity metric was a great success story. And then he said, oh, but you could have started with approximation. And then, I nearly exploded and said, yes, I mean, you could have started it, but you didn't, right? So sometimes the theory, even if it's incomputable, can guide us, in the right way. To summarize, so K is an excellent universal complexity measure and also is suitable for quantifying Occam's razor, which I will do later. Okay, so here's just one slide with the most important properties. And when I collected them a long time ago, I thought, what to put in and what to not put in. And it was pretty obvious that I should put these properties in. And it was pretty obvious that none of the other properties should be here as the core properties. So there seems to be, in my opinion, a clear divide between the core properties and all the other properties. So there was no property where I had difficulties deciding to putting in or putting out. So this is the most important properties of Kolmogorov complexity. First, every string can be represented naively by just print quotation mark string quotation mark. So what I'm presenting here, there are many different minor variations of Kolmogorov complexity. I'm presenting here prefix complexity. That means no program should be prefix of another program. That is for uniquely decoding, if you concatenate them. And if you want such a self-terminating string, you need a little bit more than length of x bits. You need 2 log L of x. You have to specify the length of the string. Okay. Then we have Kraft inequality. So because all these programs form a prefix-free set, we have this Kraft inequality here, which immediately implies that most strings cannot be compressed, that the Kolmogorov complexity is larger than L of x for most x. And okay, so here come now the maybe more important properties. So if we add extra side information, Kolmogorov complexity can never increase, because the program can always choose to ignore it. And most of these properties are very simple to prove by just, we construct a program which does the job, and then we know the shortest program cannot be larger than the one we constructed, okay? And if you want to code x and y, that cannot be easier than just coding x, okay? This is the first non-trivial property to prove, that the Kolmogorov complexity of x and y can be decomposed in first coding y, and then given y, you code x. So it's very obvious that you have an inequality, so this should be larger or equal, right? You can always decompose a coding of x and y in these two parts, but you actually have equality. Okay, so that's a non-trivial result. And indeed, sort of in order to make this, this plus also means within an additive constant. So there are always constants floating around, and that is by transforming programs and interpreting programs. So this is of the order of a compiler constant, okay? Okay, so in order to get this with an additive constant, we need this extra term, which, just forget about it. If you only care about logarithmic accuracy, which sometimes you only get, then, you don't need this, okay? If you transform information with a simple function, then you can never create extra information. So if I take a string X and transform it a little bit, and then this transformed string has also a short. So if this has a short code length, then the transformed string also has a short code length. Simply by taking the code of X plus the transformation, and then I have a code for the transformation. Okay. Okay, so here is a very, very important bound. I call this the MDL bound. So we can always code a string X probabilistically. So we dream up a probability distribution P, and then via either Shannon-Fano coding or arithmetic coding, code this string with minus log P of X bits, standard theorem. Well, we can then decode the string if we know this probability P. So we also need to know P, and P may be a complex object. So we also have to give P, which takes also a couple of bits. Okay. So together, if I arithmetically code X with respect to P, and I have given P, I have of course a code of X. So therefore, K of X is smaller. And that's what the MDL principle exploits. It looks for a class of P, and then looks for the P which minimizes the right-hand side. And you can regard this as an approximation of Kolmogorov complexity. Okay, so I said K is not computable, but it's not, totally hopeless. You can upper semi-compute it, so you can approximate from above. And even after finite time, you get the correct answer. So you run all programs dovetailing fashion in parallel, look whether a program produces X, and if yes, and it's shorter than the previous record, then you output this, and you get better and better and better. And after finite time, you have the shortest program. You just never know whether there's an even shorter program, so it just doesn't hold. Okay. And this convergence is so slow that it's useless in practice. Okay, so if you take all these properties, we can graphically illustrate Kolmogorov complexity. I have a Turing machine with a halting oracle, and this plotted me this curve here. And you see from the bounds, most strings need a code length of at least log X, just by counting. And we have the upper bound of log X to log X. So this band is very tight. But occasionally we have a string X, which is simple. And then you can code it in a much shorter way. And then you get the steps down. But if a string is simple and you modify it a little bit, or think about integers, your number, which is simple, say 2 to the 2 to the 100, it is simple, then 2 to the 2 to the 100 plus 1 is also simple. So if a string or number is simple, then neighboring strings or numbers are also simple. So if you have a deep dip, right, it also needs to be a little bit wide. Okay. Of course, it's only a very qualitative representation. Okay, so here, so those of you familiar with Shannon information theory, you have seen all these bounds here. So entropy is defined as minus P of X log P of X, sum over X, and the conditional entropy in the same way. And these are standard equalities and bounds in Shannon entropy, and they mimic very closely Kolmogorov complexity. You have the upper bound, which is log X. Then you have, if you give Y, the entropy decreases. If you want to also code Y, it increases. If you code X and Y separately, you get an upper bound. But if you code X given Y and then Y, then you have an equality, and you have an information non-increase also in the Shannon entropy. So what is actually, if the properties are nearly the same, what is the major difference? The major difference is Shannon entropy relies on a probability measure, that strings are sampled from this measure, and these quantities hold in expectation. So you see here minus log P of X, which is a code length, if you want to. But then you multiply with P of X and sum over it. So that's an expected code length. So Shannon entropy only holds, these results only hold in expectation for specific probability distribution. And these Kolmogorov complexity results hold always for individual strings. And that's its strength, because often in complex domains, if I have, AIT data and a lot of them, this is nice and holds. But if you have a single object, like a huge file, or you scrape, the internet, Wikipedia or something. So what is the underlying probability distribution? We don't really have it. Of course, you can learn it and so on, but maybe you can regard different articles as IID sampled or so. But, you have to make a lot of assumptions, which you don't have to do with Kolmogorov complexity. Okay, so that was my mini introduction to Kolmogorov complexity. By the way, if there are any questions, just feel free to interrupt me.
Someone was asking What's the mutual information analog of Kolmogorov?
The mutual information. There is what is algorithmic mutual information, and it's defined exactly in the same way. It's defined as the Kolmogorov complexity of y minus the Kolmogorov complexity of x given y. Indeed, the similarity matrix I will talk about sort of is based on this idea. Okay, so next I will introduce the universal Solomonoff distribution. And so Kolmogorov was motivated by randomness and information, but Solomonoff was interested in or motivated by AI ultimately, or by prediction, okay, or induction. And so what he did is he combined two principles, Occam's razor and Epicurus principle. And Occam's razor says take the simplest explanation consistent with the data. Epicurus says keep all of the explanations. And he combined both principles in a way of weighing different hypotheses and having a higher weight towards simple hypothesis. Okay, and well, this is all sort of philosophy in words, and you know, as scientists, we need to quantify things. And he used Kolmogorov. He didn't use Kolmogorov complexity. Sort of, he invented Kolmogorov complexity in order to quantify it. Okay, so here's a little bit of notation. Okay, L of x means the length of string, which is typically n, and then you know x1 to n is just the string x1 up to n. Most of the time, I'll just talk about binary strings, but things generalize to arbitrary strings. And x less n means you know up to n minus 1. Okay, so a very neat informal definition of Solomonoff's distribution is you take a universal Turing machine, you put random noise on the input tape, you get some distribution on the output tape, and you ask what is the probability of certain strings appearing on the output tape, right? And that is m of x, okay? M of x is the probability that the universal Turing machine with random noise on the input tape produces x on the output tape, okay? That seems to be a rather useless object, but actually has magic powers. So here's a more formal definition. So if you have this, so these are so-called monotone Turing machines, which just read the input from left to right, and then and then it produces the output on the output tape, and then at any point in time you regard what is to the left of the input tape as the program. So what we do is we sum over all programs, we produce x, and we don't demand that they hold. There's also a halting version, but since we want to do prediction, sort of we want to reproduce what happens in the past, namely x, and then it should continue. And then what's the probability that this p is on the input tape? Well, it's each bit is probably 1/2. So you get 1/2 to the power of the length of p, which is here. And then you sum over all such programs that produce a string that starts with x. Okay, that's just a formalization of this informal definition above, and there's one more which is very important. Okay, so roughly speaking, in this sum, you know, of course, you know, short program, you know, contributes a lot to the sum, and you can even formalize that. And if k index m of x is just the shortest program, it's the length of the shortest program. So instead of taking the sum, we look for the program which minimizes this. It's very similar to Kolmogorov complexity before, but here I do not demand that the program holds. It just can continue. Okay, and that's called km of x, or monotone complexity. And you can show that this m of x is extremely close to just taking the most dominant term. Okay, this is one that was for finite strings that was proven, I think, by Levin, and then it was conjectured for the monotone case that this is exactly true. And then in one of the hardest proofs I am aware of in Kolmogorov complexity, Peter Gatch in the 70s proved that actually equality does not hold within logarithmic accuracy, but it grows, I think, with a function which grows slower than any computable function, something like this, but more than a constant. So, so there are quite some subtleties and surprises in this field. Sorry?
Not just with a monotone machine.
Yes, yeah. If you just take prefix complexity and for finite strings, then it holds. Yes, yeah. Okay, which was a big surprise because you expected it transfers over. I have not met any person who understood the proof. I tried 3 times in my life to dig into, but I really couldn't get into. And I organized 2 Kolmogorov complexity symposiums in Dachstuhl in Germany a long time ago, and I asked the audience who understood the proof. So maybe it's wrong, but I don't think so. Peter Gatch doesn't make errors. Okay, so here are some relations between these complexities. So here's the prefix complexity I mentioned before, which is upper bounded by prefix code. The monotone complexity can be shorter. So for instance, have a string of all zeros, very long, but the length is an ugly number. Then I have to code the length of the string, but M doesn't code the length, it's just a print 0 loop. It doesn't care. Right? So it can be shorter, and typically, I mean, it's within a lock. Within a lock, they're all the same, right? And then so Km is just the log of this monotone complexity. So if you exponentiate, of course, if I sum over all programs, it's larger than if I just take the shortest, and then you take minus log, you get this inequality. And here, this inequality is also clear if I provide the length of x as extra information. The complexity gets shorter, but you can also show this one here. So it's a nice order here, sort of, here, all these are squeezed between k of x and k of x given the length of x. So they only differ by the information which is implicit in the length of the string, which for many purposes doesn't matter, but for some things, especially prediction, which I care about, these subtle things make huge differences. This m works great for prediction. I made this km work for prediction, but it's exponentially worse, and these other ones don't work at all. So there's a reason why we have these multiple notions. Okay. Okay. So, oops. Okay, there's an empty slide. So for meditation. And so on the end here with, I will talk about prediction and induction and mostly these things. And there are many people, philosophers, scientists who believe that deduction logical reasoning is on solid foundations, but the induction problem has not been solved. And I argued that no, induction is as well defined as deduction. So you may have quibbles with induction, but if you have so, you could have also quibbles with deduction. So, and here, I don't have really time to go through this slide. Here, I try to put left and right sort of different things, type of inference, assumptions, results, how to do inference, and so on, and the limitations on induction on the left-hand side. And I will talk about Solomonoff's distribution, and it's M of x for Solomonoff's a priori distribution, and I'll show you how to use it for prediction. And here on the right-hand side, I mean, you're all familiar with this stuff. And, if you quibble about, well, is Bayes' rule really the right rule for induction, then you can also ask if modus ponens the right thing to do deduction, right? I mean, why does A and A implies B, implies B? I mean, you can question this, right? I mean, nobody does, right? I mean, except for some philosophers, which is fine, right? But the same, with similar Frankel set theory. I mean, why this? Why not something other? I mean, it just works well in practice, right? But somehow for induction, sort of this argument that it works well in practice, is for people less convincing than in the deductive case. Okay, so let me now show you how Solomonoff solves the induction problem. So from the definition you saw that so m of x, well, this theorem on the previous slide showed you that m of x is approximately 2 to the minus km of x, k of x. So don't bother too much. So this shows you that it assigns high probability to simple strings and low probability to complex strings. So it incorporates sort of Occam, but it discards no string. So it also incorporates epicures. I mean, I know in the end, sort of, we want to have a probabilities over hypothesis, but I come to that. Okay. Yeah, I said this. So how do we do predictions? So first, so let's assume that m of x correctly describes our prior belief in a string x. Yeah, so a priori we believe, a string of all zeros, that can happen quite easily. A string of pi is less likely, and if there's a random noise, it's even less likely. This particular, that's important. Of course, random strings are maybe as popular as deterministic strings, but it's about a particular string, right? So then we take the ratio. So that gives us the probability that x, the belief probability that x is continued by y. Okay, and if you crank a little bit the mathematics, what you will get is that m of y given x is then also just 2 of minus k of y given x. Okay, so that means that you have a string x, and you look at possible continuations y, and you ask which ones are more plausible, and the ones which are similar to x, similar in the sense that there's a short program of converting x to y, are more plausible. So here is sort of, this is a prior towards that the future is similar to the past, but this similarity is a very, very general similarity measure, not similar in any naive way, so that you have a Bernoulli theta and then the future needs to be Bernoulli theta or so. Okay, and anyway, I mean, if you use this on the right hand side, it wouldn't work, right? This is just to give you an intuition what's going on. Yeah.
When you say prediction, what we predict the next things in the output of the.
Yes, so we have a string x, and you want to predict what comes next, right? You have 0, 1, 0, 1, 0, 1, 0, 1, what comes next? Well, so in the Solomonoff, in the M case, you have the history, the x also on the output. You just sample random noise on the input until you sort of accidentally sort of get this string x right, and then you continue and see what it predicts. In the Kolmogorov complexity case, x would be the input and y would be the output, but this doesn't work. I mean, this is for technicalities, it doesn't work, but intuitively, yes, you can envision x on the input and then y in the output, although it doesn't really work like that. But for stupid technical reasons. So I think I will skip over this. So there's Solomonoff's theorem to prove is a little bit, involved, not too much. So I simplified the proof a lot. So if you look at Solomonoff's original paper, that is quite unreadable. If you look at Lin Vitani's book, that is much more readable, but then we went over it, and in his third edition, the proof is really nice now. But for the deterministic case, if your sequence is generated by some deterministic computable process, you can easily show that if you take m of xt given x less t, so a one-step prediction, it's the probability that it predicts xt, you take 1 minus, so that is sort of the error it makes, and then you sum over all time steps, then this is bounded by the complexity, description complexity of this string. So if you can describe a string in 100 bits, then roughly speaking, if you use m for predicting this string, it makes around 100 errors. Okay, you don't know when and where, but roughly speaking, okay, which makes sense. I mean, if you describe something in 100 bits, but you don't know this 100 bits, you have to learn this sort of by making some mistakes, and that is very easy to prove. I mean, the proof is essentially complete here, and then you can generalize that to the stochastic case. In the stochastic case, you don't predict the next bit, for sure, but predict what is the probability of the next bit. Assume you have a, Bernoulli 0.7 process, and then you ask what is the probability, but you don't know that, right? And you just observe zeros and ones, and you ask what comes next, and then Solomonoff will predict, with probability 0.65, a one comes, and then it will converge as, to 0.7 also fast. Yep.
This is possibly an question. Intuitively, do we this random noise is coming into the Turing machine,
yes,
producing some output, and are we basically trying to infer the structure that's coming out as if the thing is Turing machine is running some program? So nature is the analogy of prediction. Nature is running some program. The output some.
Yeah, it is. So it's essentially I mean, our world looks stochastic. I mean, and maybe it is truly stochastic. So what we want is we want a description, a probability, a computable probability distribution which describes this, and you can separate that into a program. So you can always generate random noise. Well, any random noise you want to generate, you just need fair coin flips, and then you process these fair coin flips somehow. Yeah. And in a purely deterministic world, you don't need the random noise on the input tape. You just need your program.
And then the simplicity bias is coming like the shortest program that describes this thing you got. Yeah.
Yes, well, in Kolmogorov complexity, you pick the shortest one. In the Solomonoff distribution, there's a bias towards the shortest one. In the explicit sum formula, you saw it by 2 to the minus L of x. In the piping random noise to the Turing, universal Turing machine, if the input head reads only a little, then there are lots of programs, right, which start with this short initial part compared to if you read a lot.
So it's quite analogous to machine learning then, where you have, you know, you could, like you were saying, you could represent a distribution with the inverse CDF or something, and it's like you're trying to learn.
Yes.
Thing that transforms the noise, like generative modeling.
Yes, yeah, very similar. It's just sort of a universal here. Yeah. Okay. So the important point here is to notice that M doesn't know anything about the world. You feed it the first digits of pi, and eventually, and actually with the best possible convergence rate, yeah, it will predict then the next digits of pi. Or if you feed it the stock market, and if there is any computable predictor of the stock market, then Solomonoff will not be significantly worse and asymptotically equally good, right? So weather data or whatever. Statistically, not computationally, of course. Okay, so yeah, I mentioned already it converges rapidly to the true distribution. It solves a lot of philosophical and statistical problems, which I don't have time to go in. I mean, in philosophy, you have the zero prior problem, old evidence problem, and so on. Or the Blake-Ravens paradox, confirming universal hypothesis. From statistics, you know, we want reparameterization invariant sometimes. If you know MDL and Jeffreys prior, which is reparameterization invariant. If you have a, roughly speaking, a compact class, but it doesn't work for non-compact classes, you can show that Solomonoff is also reparameterization invariant. And you know, it has a lot of nice properties. So I've written a long paper summarizing all these the properties 10 years ago with a student of mine. So another critique is often, but we have prior knowledge. So I mean, Solomonoff ignores all this prior knowledge. Well, you can easily put that in, and there are multiple ways. One is, instead of taking, you know, Solomonoff or Kolmogorov as it is, you take your prior knowledge as extra information on an input tape, like conditioning on it, like here condition on Y. That is one way. Or you don't even have to do that. You know, if this is my data and this is my prior knowledge, I take my prior knowledge and code it in any way. I mean, nowadays all prior knowledge is somehow, you know, data anyway, and I just prefix my real data with my prior knowledge. It doesn't really matter that it's, you know, different types and different organization. Solomonoff and Kolmogorov figure all this out, right? If there's a computational structure in your prior knowledge which is related to your data, it will figure it out by itself, right? You just take your prior knowledge and prefix your sequence. For instance, I think I'm really running out of time. So it's another critique. Okay, what if I give you here 1 1 1 1 1? What comes next? Most people would say 1, right? And it's very natural, and I think, I mean, that's the sensible answer. If you take Kolmogorov complexity, it has its additive constants, and you should be able to construct a Turing machine which is still reasonable, which predicts 0. And then you would say, oh, what is going on here? So that's not good, right? So so why do we after 5 once have a strong belief that there's another 1? Well, the reason is we have seen in our life a lot of constant sequences, right? And not, maybe not, you know, in cases of ones, but other constant sequences. So if you take this experience, take your lifelong experience, put it in a big string, and prefix it to the 1 1 1 1 1, it will see, you know, there's lots of constant sequences. So it would have a subroutine of, you know, predicting constant sequences. And then independent of the choice of the universal Turing machine, even after 5 bits, it will correctly predict, you know, another 1. So that's a solution to, say, predicting short sequences. I mean, Kolmogorov complex and Solomonoff is really meant for predicting long sequences, because always you have this compiler fudge, which is about, you know, maybe 10,000 bits, maybe even 100,000 bits. So you really need data which is beyond, you know, 10K, 100K for this universality claim to make sense in practice. Okay, and yeah, and there are various ways to approximate that in practice. So MDL and MML is one, using standard data compressors. So who has not heard about context tree weighting algorithm? Okay, so this is one of the most amazing. So okay, if you like Bayesian statistics and you're interested in sequence prediction or data compression, you really need to know CTW. It's a beautiful construction of Bayesian mixture over all variable Markov processes, which is a double exponentially large class, but you can average that in linear time. It's beautiful in theory and works also extremely well in practice. And nobody knows about it. It just won a prize in 1995, and it's patented, and but it was engineers, so maybe that's the reason. In IEEE transaction of information theory, I think. Okay, so Martin Löw randomness. I have till 11:15, right?
I would say like 10 minutes.
I have 10 minutes left.
Yeah.
I thought I have an hour.
It's 45.
I started 10 past.
Yeah, it just stop. Yeah.
I should have half an hour left, right? No?
No, you have, I would say maximum 15 minutes.
Okay. Okay, no Martin Löw randomness. Goodbye. So that's about, in classical statistics, or even Bayesian statistics, you cannot ask even the question, is this string, you know, is this string here, you know, random, maybe this one. You cannot ask this question, okay? And Martin Löw randomness allows you to ask this question and also answer it. And roughly speaking, if a string is incompressible, so if the Kolmogorov complexity of X equals the length of X, then this string is Martin Löw random or simply random. And then if you ask classical probability, so is the number of ones and zeros equal, you know, what is, you know, the deviation from it, what is with pairs and so on. So you ask standard tests, you know, randomness tests. You can show that Martin Löw random sequences satisfy all computable classical statistical tests. So it's really random in the sort of most strongest sense. If you want to, you can say it's a pumped up version of pseudo randomness. So pseudo random sequences satisfy all polynomial time randomness tests. But you know, in exponential time, I can figure out the random number generator and see that it's not really random, but I cannot do that in polynomial time. And here it's just a level up, so no computable process can figure out. So for instance, the halting, not the halting sequence, but there are sequences, say the Chaitin's omega, right? In principle, that's limit computable, but no computable randomness test can see that this is actually sort of limit computable. Anyway, I have to skip this. I think you're cheating on me in time. Look at the schedule. Or did you change it? So I also skipped the minimum description length principle because we have at least two other talks here about this. So here I try sort of a derivation based on you know, starting with Kolmogorov complexity. And here's another derivation starting from Bayes' rule. So you have a prior over hypothesis, then you have a likelihood function, and then with Bayes' rule you get a posterior of the distribution. And then you take the logarithm, and then you call the log likelihood, that is the code length of your data. And the log prior is the code length of your hypothesis. And then instead of taking a Bayesian mixture, if you take a maximum posterior approximation, which in the minus log gives you then a minimum, which then gives you sort of the MDL principle roughly out of it. So here you have a code length of X with respect to a distribution nu, and then also the code length of nu. And you look for distribution in a class M, which minimizes this, and then the MDL principle claims, you know, that's a good distribution to use. And you can prove that this is indeed the case. Okay. So that's an example of polynomial fitting. And maybe let me say the only thing I want to say is that in practice, often we have continuously parameterized model classes, so with real parameters, when the code length of a real parameter is in principle infinite. But if you take this model and you wiggle a little bit on the parameter, a tiny bit, the model prediction doesn't change much. So the minus log probabilities or arithmetic coding also doesn't change much. So you only need to code these parameters to a certain accuracy. Okay. And so for IID data, we know we can estimate a parameter from sample size n to accuracy 1 over square of n, and no further. In order to encode a real number to accuracy 1 over square of n, I need log square of n bits, which is 1/2 log n. And you can show sort of more formally that indeed it's sufficient to code each real valued parameters with 1/2 log n bits. So if you have, say, a model class like polynomial fitting, you punish each parameter by 1/2 log n. So that's called crude MDL. And then you can have correction terms, which depend on the square root of the determinant of the Fisher information matrix, and so on. Okay, so let me give you one amazing application of Kolmogorov complexity. Here the question is a little bit different. We ask, when is a string X similar to a string Y? And this conditional Kolmogorov complexity seems to fit the bill quite well. If X and Y are similar, then there's a very short program to transfer. And if they're dissimilar, well, then there should not be a short program. Because, I mean, even say if, X is picture and Y is the complement of the picture. I mean, they're extremely similar, right? It's just a complement, right? And Kolmogorov complexity will, of course, figure this out. So that sounds like a good candidate for a universal similarity. And by the way, in machine learning, it is often a big problem what similarity measure you use. I mean, you have two images. When are two images similar? And all kinds of more sophisticated metrics. And this is sort of a universal solution to the problem of a distance between two objects. Okay, and so X is very similar to itself. And indeed, K of X given X is 0. If I process X, flip the bits, all of them, or something, or it should be still similar, and that is also the case. And a random string, should be dissimilar to any other string, and this is also indeed the case. So that seems good, but it's not symmetric, it's not computable, and it's not properly normalized in a sense I come to that in a second. But all these problems can be solved. If symmetrization is similar, you can just take K of X given Y and K of Y given X and the max. You could think of similar options, but sort of this is the neatest one. It's not the only one which sort of works, but this has very nice properties. And then, if you have two very long strings which differ by 50 bits compared to strings which are just 100 bits long and differ by 50 bits, you would say these long strings are sort of more similar, right? So you want sort of the relative change. So that's the reason why you normalize by sort of the length of the string, or more appropriately, the Kolmogorov complexity. Okay, and if you do that, you get a distance measure, and you can actually show that it has all the properties of a metric, which is very nice. So Lee and Vitani say it's a metric within an additive constant, but actually you can get rid of this additive constant in this case, or make it a real proper metric in the mathematical sense. Okay, so but it's still not computable. So the last thing we have to solve is the computability, and here we are very lazy. We just replace. So formally, we replace the universal Turing machine by other Turing machine, and in practice, we just, this is the length of the shortest program with respect to t. What is that? This is actually a program which produces X. Is actually a self-extracting archive. So what we do is we just take standard practical compressors like gzip or lentil-zip or the CTW and compress the X and use this as an upper bound of K of X. Okay? Or I mean, sort of, yeah. Okay. So now it's even computable. And so now assume we have, do I have the, yeah, if you have multiple objects now, so sorry, I should put the index up. So X1 is now a string and Xn is a string, so different strings. and I do pairwise comparison. So I have a distance matrix between string xi and string j, and I could present you a big matrix, but that's not so nice. So you could look at a minimal spanning tree, roughly speaking, or minimal spanning tree, which approximately represents this matrix. And if you want internal nodes, that's actually an P-Conv problem, but you can approximate this. And so Celebrasi and Vitani, they applied this to a lot of domains. I just present two of them. One is mammals. So they took the mitochondrial DNA of 24 mammals. The DNA, is just over base pair ACGT. So it's, you can code in 2 bits. So it's a binary string. You do the pairwise distances, and then you look at this big matrix and look at the closest one, second closest one, and build a tree. And you get this tree here. And this perfectly reproduced the phylogenetic tree, which biologists sort of, unearthed in, decades of study. And, there's and they use ESIP, I think, or Lempels, or GSIP, I can't remember. And definitely there's no biological knowledge, in these compressors. And carp is not a mammal, and you see it's, far out here. And then you see sort of all these Australian rodents are here, and then the primates are here, and, others, and, bears are much closer to, to themselves. So perfect reconstruction. Then they did it with language. So they took 60 or so European languages, and they took the Declaration of Human Rights, which is written in virtually all languages, and nearly perfectly reconstructed the language phylogeny here. I think there are 2 errors here. So Greek is always a problem because they're different alphabet and so on. Okay, so can you double check the chat schedule? Okay, so let me give you some further applications of all this. So that is here my favorite, naturally. Oops. So Solomonoff, I argued, solves the prediction problem, and a prediction is a big part of being able to act intelligent, but you have to do something with these predictions, right? So you have to make decisions. So there's something more to do. And if you act, you influence the world, and that gives you feedback. And Solomonoff in itself sort of can't deal with it. And so here's just the general agent environment framework. You have an agent that acts, then the environment produces some observation and feeds it back to the agent. Okay. In order to specify what we want this agent to do, we use a reward signal, and just occasionally, reward and punish the agent. Like if you play chess, you give it a +1 when it wins and -1 when it loses, and so on. It's sort of the minimal feedback we have to give an agent in order for the agent by itself to figure out what we want it to do, right? I mean, there are also other paradigms like supervised learning, where you have a real teacher, which is much more laborious. And then there's unsupervised learning, but this, in this way, you never can tell the system what to do. It's just more like exploratory analysis. Okay, so, and let me give first, before I define the most intelligent agent, define what intelligence is. Okay, so here's a formal definition. So if an agent or policy is a mapping, it has in the past received some observation and reward and performed some actions. So that's a sequence of this, and it wants to perform the next action. This just means stochastically. Okay, and then the environment reacts. So given this history and the last action of the agent, it produces a new observation in reward. And then you are in this cycle. And what is a performance measure? Well, we look at all the rewards summed from time to 1 to infinity from this policy and this environment. And if it's stochastic with the environment, we take the expectation. And that gives us the value of policy pi in environment mu. Okay. And we want to maximize that. Yes? Yeah, you have to discount, but let's take it offline. Yes. Either you take finite horizon or you discount, so I just skip over all these things. In this way, we put this discounting in the environments themselves, which is sort of a neat trick. Okay. So, but the true environment is unknown. Okay, what do we do? Well, we have prior beliefs a priori over which world we are facing, and we should have a large prior over simple environment. So we measure the complexity of environment by Kolmogorov complexity, and we take the average over all these values, right? The agent pi may face environment mu. A priori, the belief probability that it faces environment mu is 2 to the minus k of mu. We sum over all probabilistically computable environments, and we get this epsilon of pi, which we call universal intelligence measure. Okay, and while Shane Lack has written a whole PhD thesis about it, so you can read about that. It's arguably contains all properties an intelligence measure should, or it measures all intelligence traits, all traits which we usually associate with intelligence. And well, if you trust this intelligence measure, well, then we just take the argmax and you get the most intelligent agent and you're done. AGI solved. Okay. Apart from the minor problem that everything here is incomputable. Okay. But that is my claim, that sort of we have this gold standard. So if we had infinite compute, AGI would be solved. And in a sense, we're all striving towards it. And you know, some people argue it's pretty useless, but I argue it's pretty useful. So, I mean, think about, you know, a long time ago, minimax to the end of the game like chess, right? That's the optimal strategy, but it's completely infeasible. But, you know, everyone tries to, you know, aim at, you know, this. And this is just extended from minimax to expectimax, and then from expectation with respect to a known true distribution to an unknown distribution. So essentially what happens here is, there are different formalizations. Maybe I show it in the next slide. You replace this known mu by essentially Solomonoff's distribution. You don't see that here, but you see it in the next 2 slides or so. Next, again, okay. So this is very abstract here. So AIT is an argmax over policies and so on, but you can sort of drizzle all this out and write this out explicitly here. And here, everything is really there. Right. The only thing which is implicit is what is a universal Turing machine, which is, you know, unfortunately not so trivial. But everything else is here. So at time step k, the agent wants to perform an action. And what it does, it looks at the future rewards, potential future rewards. It doesn't know them, but it has a belief over it. So it takes a possible environment P, looks if I take this action A's, it receives some observations O's and R's. And the belief in this is 2 to the minus length of P, according to Occaming Epicurus. So that's sort of the predictive part here. And then it tries to take an expectation, which is these sums here. Okay. And then it tries, of course, to maximize reward. And this is these maxes here. And it does that like a minimax search in an expectimax way. Okay. And then you get the action. Done. Okay. So, apart from computational issues, and so, you know, Levin maybe was the first one to use this universality idea and sort of turn it on its head and invent this universal search. Jürgen Schmidhuber was maybe the first one who practically implemented this. And he solved, you know, some non-trivial problems, you know, mazes, towers of Hanoi, and so on, in this way, making it adaptive. And I generalized that. I mean, sort of Levin search works for problems where the solution is easily verifiable. But we know in games, you know, games can be p-space complete, and the solution is not even easily verifiable. I extended that to arbitrary problems, even beyond NP, which is important for AI. And, you know, ICTL, which I will not talk about, is one of these approximations. But here's one. Again, I will skip over sort of where we replace the planning by Monte Carlo tree search and the Solomonoff distribution actually by this CTW, which I mentioned before. Okay. And you do that and you use this agent. It's the same agent. And this agent is not told what is the goal of the game, what is even the game. It just gets bits in and bits out, and it learns to play, you know, these admittedly simple environments, you know, like tic-tac-toe, coon poker, and, you know, even Pac-Man it performs, you know, it improves somehow. Okay, so I skipped some applications. I mean, there are many of them. There are some neat, so sometimes, proofs in mathematics are just existence proofs, and you can make these proofs constructive. Often the existence proofs is, if you look at it, it's a counting argument, and the object which satisfies this property is sort of a random object, which you cannot really grasp. But with Martin-Löf randomness, we have a notion of, we take a string which is incompressible. Of course, we also cannot really have it in our hands, but this is this single string which Kolmogorov complexity is the length of the string, and for this string, something holds, rather than there exists a string for which something holds, right? And you can make a number of proofs, for instance, that the infinite many primes, quantitative. You can quantify Gödel's incompleteness theorem, that essentially essentially all statements in mathematics are formally undecidable, as long as the statements are longer than the length of the axiom system, roughly speaking. So in physics, I mean, there's something like the Maxwell daemon, which seems to defy the second law of thermodynamics, but with Kolmogorov complexity, you can fix it. Reversible computing is interesting, and you need sort of to store all these bits, and you cannot delete them. And the question is, what is the minimum number of bits you need to store in order to do this reversible computing? And with Kolmogorov complexity, you can show that it's a very small number of bits. So in principle, you can make every computation reversible. The universal search I mentioned, and this universal serial arithmetic, Lien-Vitani applied, and Cilibrasi applied to many other domains. Okay, so here's some references, and I'm finished. In time, whatever the correct time is.
So I was waiting for the sign for the coffee to come in, so there's no coffee, so you can talk as well as you want.
Now maybe I can take questions. Have you checked the schedule?
Yeah, the schedule, yes, we are just on time for the schedule. Yes, so there are 3 questions.
Yep.
Sorry. Is that for the computable approximations to the Kolmogorov? Do they have an advantage to Shannon information? Like, would you say that?
Well, there are some which you could argue are quite close, which are, say, the CTW, for instance, is a Bayesian mixture of a variable order Markov processes, right? And so we have sort of then sort of a probability distribution, and then it gets quite close or similar to sort of properties of Shannon information. But then there are other compressors which are like Lempel-Sif or so, which are not based on on probabilistic arguments, where the connection is probably quite stretched, if there's any.
I guess maybe what on one of the early slides you said that basically the Kolmogorov complexity is superior to other notions of information.
Yes.
Like, what is the key thing that needs to make that?
Well, the key thing is that I can ask about the complexity of the string itself, right? And I don't need to sort of invent a probability distribution and then ask about, does it satisfy certain randomness properties? So that's a key advantage. So if I have a long sequence, so look, if I have AIT data, then the name already says it's probably sampled from the distribution, because I have multiple samples. I can maybe infer the distribution from the data. But if I have one long string, right? What is the correct a priori distribution? Maybe I can try to chunk it into pieces and then look at the statistics. And of course, there are various ways of trying to come up with distributions and in machine learning, but that's a really hard problem. But with Kolmogorov complexity, there's no need of defining a distribution over strings. You can just look for the shortest program, or then the approximation of it, which reproduces sort of your data, and then you can use this for making inferences.
So I guess a related question is that.
May I ask one question?
I think that when you said in Martin-Löf randomness, there's no way in without Kolmogorov complexity to define whether a string is random or not.
Yes.
I think you can do a hypothesis test to say, does this string come from a certain distribution or not?
No, but you can also only falsify that it does not come from the distribution. You can never confirm that it comes to the distribution.
Right.
Because I mean, think about a Bernoulli 1/2 process. I mean, okay, you want to test whether something is Bernoulli 1/2. What test would you do? Okay, first you take the frequency of ones and zeros. Okay, then maybe you should take 0, 1, 0, 1, 0, 1 has the same number of ones and zeros, right? Okay, then I take maybe pairs, right? And then maybe triples. But then there's a law of the iterated logarithm. And, you know, there's a long history. Wald and Will and others, you know, try to, you know, come up with universal tests to separate Bernoulli 1/2 from not Bernoulli 1/2. And always the next guy came and, you know, found, you know, a test which where this fails, right? And then Martin Löw was the final one who was successful. And I mean, Martin Löw randomness is defined actually in form of tests. So he looks for all possible randomness tests, and there's a formal definition, right? I mean, sort of, you know, it should blah, blah, blah. He limited itself to computable tests, because if you take all tests, you know, this whole breaks down. And then from all the computable tests, he constructed one universal test and said this universal test, you know, tests actually for all these computable properties. So that's how Martin Löw randomness is defined. But then you can show that a sequence is Martin Löw random if and only if it's compressible. So it was not defined in terms of compressible, but sort of it is equivalent.
So may I ask a question? Okay, all right. Sorry.
The RL framework, AXE, I guess.
Yes, yeah, AXE, yeah.
AXE, right. My experience, for instance, with the similarity metric is that even though you could just plug in zip instead of Kolmogorov, to actually show that the approximation is well behaved, it gets very hairy. So is there a similar gap in AXE? Can you sort of prove that it actually approximates Kolmogorov complexity in a reasonable way, or that it's well behaved, or is it just sort of?
Well, I mean, the AXE itself doesn't use any approximation, so that's based on the exact Solomonoff distribution. So there's no approximation here, and we can prove. So for the Solomonoff prediction itself, you can prove extremely strong statements about convergence rate and so on, with really no caveat, essentially. I mean, there's always ways to quibble about things, but okay, you can really forget it. For the AXE model, the statements are weaker. And one problem is we still actually do not even have a good notion of optimality. So which is on the one hand strong enough so that if something satisfies it, we are convinced that this agent is really good, but weak enough so that some agent at all can satisfy that. So we have, you know, notions of regret and pack bounds and so on, but you can, you know, you can fool them in an agent who is eager to jump into traps, you know, is optimal with respect to regret, and all these kinds of things happen. You could, of course, be a hardcore Bayesian and say, look, I have a Bayesian, I have a prior, I have a likelihood, and Bayes is optimal by construction. So if you're hardcore Bayesian, then AX is optimal just by construction. And I'm sort of pretty hardcore Bayesian, but not that hardcore. I still, you know, would like to have some other properties to be proven, like, you know, frequentist statements. But it's hard, but we have them. And with respect to your question about approximations, depends on the type of approximation. For instance, the CTW, which I mentioned, has beautiful theoretical properties. And I mean, already Willems and the other authors proved bounds. Mostly Joel Van Ness, or with Joel Van Ness, we extended this scheme, and you can prove very similar bounds to the Solomonoff bound, but of course for more limited sources. For instance, the source need to be ergodic and stationary, and then you can prove corresponding bounds. But if then the source is the digit of pi, the CTW approximation will fail.
May I ask a question?
Please copy it from the main hardware campaign. It's only 5 minutes break, so there's a question. Do you want to ask a question? 5 minutes break. Yeah, maybe I just have 10 minutes. Let's say 10 minutes break. So we resume at 11:20. So there's someone actually wants to ask a question.
Yes, maybe I should. You can come on.
Yeah, maybe.
Maybe just put it here.
Yeah. Is he answering from there? Or I don't know.
No, I don't know. You can ask the question now.
Can I answer the question?
Yes.
Oh, yeah, can you mute yourself? Just mute yourself.
I think I am.
No, I'm not muted.
Ah, wait a second.
Can I ask now?
Yeah.
I'm muted now. Oh.
Yeah, you are muted, Amir. Can you unmute?
Yeah, I was not sure. Okay, now it feels like there's no echo.
Yeah.
Sorry, glad I can speak. I was just wondering if there is any like upper bounds on Kolmogorov with the discrepancy theory, because like discrepancy is sort of goes in the direction of measuring randomness, but very simply. But the advantage is that it's computable. I was wondering if there are any bounds.
Oh, actually, I don't know what this discrepancy theory. I don't know what that is, to be honest.
I mean, for instance, like if you have a bunch of like think about zeros and ones and minuses, like ones and minus ones, and then for example, you can say it's random if for any like substring of this, the sum is always close to zero. Or like you can also say like an arithmetic, like progression, that if you go in like steps for any like arithmetic progression of the sums, it's always close to zero. So that's sort of like saying that it's like if you put them in a like a two,
but that sounds so looking at subsequence of a sequence and checking whether this also has the randomness properties, that sounds very similar to what either Van Mises, Wald, or what was the third guy I forgot, did a long time ago. And if you appropriately limit, I mean, the choice function, I think it was a choice function, then it can work in the sense that you can test for, you get a quite strong test, but it is still weaker than Martin-Löf random. So there's still certain strings which are not random, but which cannot be detected by any such test based on, I think it was called choice functions. So look at this old literature, whether, and maybe what you're talking about is different, but it feels like, choosing subsequences and then checking for it is like Van Mises, Will, and Wald. These three guys tried before Martin-Löf then came in.
Okay. Yeah.
So
thank you.
Is there still time to ask a question?
Could I also? Sorry.
So if I transform a string X through two deterministic programs, say P1 and P2, and if I compute the approximate K values for P1X and then P2X, so by comparing these two values, can I infer something about the complexities of the transformers, something about the complexities of the programs P1 and P2, and something about their information processing capabilities also?
Okay, sorry, I didn't get the P1 and P2. So, I mean, I had this statement, if you transform X by a simple program P, the complexity never goes up. I didn't get how you take two transformations of X, P1 and P2, and then you want to compare them?
Yes, and then I compare the K values, the Kolmogorov values for the P1X and the P2X. So by comparing these two values, if I can I predict something about the complexities or the processing capabilities of the P1 and P2? And obviously, I would be having many transformed strings to be compared with.
I mean, you should get bounds, right? I mean, we know that K of P of X is bounded by K of X plus K of P. And if it's significantly smaller, then this P sort of lost a lot of information in X. And if for P2 it's not significantly lower, then you must have pertained more information. Maybe that's what I can come spontaneously up. You probably get some, you should be able to get some one-sided information out of it because it's only bounds. You know, maybe send me an email with the exact question and I have a look at it.
Sure. So does this mean to see the distribution of the k values? So in your presentation, you talked about the universal distribution. So does the mean of the universal distribution is same as the distribution of the k values?
You mean the mean with respect to the universal distribution is the same as the mean?
Same as the distribution of the k values, say for a, I mean the distribution of the k values for the different programs. Say?
I think we don't have much time here, right?
Yeah,
so maybe I mean we can have a also a video chat offline. You know, from Wednesday on, or you send the question by email to you. That is maybe a little bit too complicated to answer here in a couple of minutes.
Yeah, sure, definitely. Thank you, and thank you very much. Thanks,
yeah.
Thanks for such a great presentation.
Yeah, thank you. Yeah, but please send me an email and we can continue the conversation.
Sure, thank you.
Yeah, okay. So we'll resume in 5 minutes. Yeah, and basically technically in 3 minutes. Yeah. Okay. See you in a bit. Yeah.
Okay.